Greetings. So, welcome to today's class. So, if we quickly recap what we were learning in the previous class, like we were looking at the unit step response of the standard underdamped second order system. And we derived the corresponding expression for the unit step response. And we found that once again, it contains exponential terms, and the exponents are the poles minus zeta omega and t plus j omega plus or minus j omega d. Of course, the reason e power j omega d or e power minus j omega d doesn't explicitly come in this expression because they are accounted for in terms of cos omega dt and sin omega d, right? Through the so-called Euler's relationships or complex exponentials. And we can see that this particular expression shows us that, the output of the system tends to 1 as t tends to infinity. And although there are oscillating components here, they are multiplied by e power minus zeta omega t. So we are going to have oscillatory components that are going to that are going to be dampened with time, right? So they're going to be attenuated. So consequently, we'll have an oscillatory response as shown in this figure, and the oscillations will dampen out, and finally we will reach the steady state of 1 asymptotic. And then, based on this unit step response, we define certain parameters that quantify the response of underdamped second order systems. We started with rise time, which is the time taken for the output to reach 100% of the steady state output for the first time. Depending on the convention, this may be 0 to 95%, 0 to 90%, 10 to 90%, and so on. Okay, different people may take different ranges for defining the rise time, but we have done it this way, and we have derived an expression for the rise time. Then we have essentially derived what is or defined what is called as the peak time. I left the derivation to you. I hope you are able to do that. So peak time is the time at which the first overshoot peak comes, right? So that is the maximum value of the output. So that expression for peak time is pi by omega d. And then based on the speed time, we have something called as a maximum peak overshoot, which sort of quantifies by how much am I overshooting, right? When we are dealing with this peak time, with this response function. So that comes out to be the expression shown here, e power minus zeta pi by square root of 1 minus zeta squared, right? So minus zeta pi by square root of 1 minus zeta squared is the exponent of the exponential term, okay? And we saw the trade-off between the rise time and the peak overshoot. If we decrease the damping ratio, the rise time decreases, so faster response, but the overshoot increases. If you increase the damping ratio, the rise time increases, but the damping ratio, but the overshoot decreases. Then we also looked at settling time, which is the time taken for the output to settle within a band of within around the final output, steady state output. So if you take a 2% band, the expression is 4 by zeta omega, and if you take a 5% band, it's 3 by zeta omega. Okay, so this is what we have done. Okay. So any questions based on what we learned yesterday before we move to today's topic? All right, okay. So today, let's start with a question. Okay, so by the way, before I forget, I should once again add that I have now updated the classroom page with the syllabus of the course. It was pending from my end. Sorry about the delay, but now I have updated it. So please do check it. Okay. So the question that we need to ask ourselves is that we are going to start off with in today's class is the following. What happens if zeta is equal to 0? That means that damping ratio is 0. So such systems are what are called undamped systems. Okay, so there is no damping per se. Okay, so what happens in such systems, right? So if I have no damping, obviously the Planck transfer function becomes omega n squared divided by s squared plus omega n squared, right? So because zeta is anyway 0, so the 2 zeta omega n s term vanishes. So once I get this, if I want to figure out the poles of the transfer function, I have to solve s squared plus omega n squared equals 0. So if I solve this, the poles are going to come at plus or minus j omega n. So I'm going to have complex conjugate poles, right? So on the imaginary axis. So now we can observe that like these are non-repeating poles on the imaginary axis, and consequently, as we already discussed, so if we have non-repeating poles on the imaginary axis with no pole in the right of plane, that system is going to be marginally stable, right? And the system output will become unbounded for cos and sine sinusoidal signals whose frequency, angular frequency, is equal to the magnitude of the poles. So here the magnitude of the poles is omega n. So consequently, for u of t to be equal to cos omega nt and sine omega nt, the output will be unbounded. Okay, so that's what will happen. All right. Okay. So for these outputs, specific inputs, the output become unbounded. So this also sort of gives us a feel of why this omega n is called as natural frequency. So let us address that question. Okay. So we would want to ask what is natural frequency, right? So what is the notion of natural frequency that we are aware of? What, in your opinion, is the definition of natural frequency?
So frequency in the absence of any damping force.
Okay, so frequency in the absence of any damping force. Okay, good. So can you complete that answer? No.
Sir, basically it is the frequency of the system due to its self-weight without any external force acting on it.
Okay, very good. So I think that sorts of, I think both your answers complete the answers. Okay, that's very good. So both of you have given one half of the answer, right? So let's put them together. Okay, so natural frequency, it is the frequency at which the undamped and unforced system would oscillate when perturbed. Okay, so there is no explicit external input per se, but then like what we are doing is that like we are just perturbing it from its initial state. Okay, let us say the system is in some equilibrium state, right? Let's say we have a mass spring system, right? So what I do is that I just displace the mass a little bit. Then the question becomes, what is the frequency with which the mass oscillates, right? So let's figure that out. So let us consider the standard 1 degree of freedom mass spring damper system, right? So whose governing equation is something which all of us know about, right? So let us consider the 1 degree of freedom mass spring damper system, whose governing equation is the following. Governing equation is, as we know, it is mx double dot t plus cx dot t plus kx is equal to f of t. Okay, so now see, all of us know, right, that for this particular system, the natural frequency formula is square root of k by m. Okay, so that is something which all of us are aware of. Now the question arises, how do we get here, right? So that is the question that we need to ask ourselves, right? So let's apply the definition. Okay, so natural frequency is the frequency at which the unforced undamped system will oscillate when perturbed. So we consider the damping to be 0, right? So X dot is not 0, but the damping force is 0. So C, let's say we take C to be 0 and F of T to be 0. Okay, so that's what happens. So if I do this, what will happen is that like the governing equation simplifies to be mx double dot T plus K times X of T is equal to F of T. Okay, so that's what you do. Sorry, not F of T, it will become 0, right? Because now there is no external force per se, right? So, sorry. So this becomes equal to 0. Okay, so once this becomes equal to 0, let's now try to solve this, right? So we can do it in many methods. Let's apply the Laplace transform, right? So apply Laplace transform on both sides. So if we apply the Laplace transform on both sides, what do we get? We will get m times x double dot will become s squared x of s minus s times x0 minus x dot 0. Okay, so that's what will happen to the first term x double dot. Then we will have k times x of s is equal to 0. Okay, so this is what we will have. Of course, now we are not going to substitute initial conditions to be 0, right? So we substitute initial conditions to be 0 only when we are looking at the transfer function, right? So now we want to figure out what happens when the system is perturbed. And the way we perturb the system is by giving a non-zero initial state, right? So we displace the system a little bit and let it oscillate. So let us solve this. So we are going to get ms squared plus k times x of s is going to be ms times x0 plus m times x dot 0, right? So very straightforward. I'm just simplifying things, right? So by now, I'm sure all of us know what to do. So we just take it to the other side. So this will give us s times, I take ms squared to the other side. And then like I'm going to essentially split it into two terms. So we will have s times ms times x0 plus m times x dot 0, right? Divided by ms squared plus k, that's what will come out. So I divide both the numerator and denominator by m, and then we split the terms separately. So this is what will happen. So I will get x0 times s divided by s squared plus k by m, okay, plus x dot 0 times 1 divided by s squared plus k by m. Okay, so this is something which we, right? So pretty straightforward. Now we are just going to take the inverse Laplace transform. Before taking the inverse Laplace transform, let's do one more step. Okay, so just for simplification, so x of s will become x0 times s divided by s squared plus k by m. So the way I am going to rewrite this as s squared plus square root of k by m whole square. Okay, so you will see that why I am doing this, right? So this is very straightforward. So then the x dot 0 term, what I do is that I divide and multiply by square root of k by m, so that like I make it consistent with the formula for the Laplace of sine omega t, right? So essentially, I get it as get it in this form. Okay, so all right. So this is how I get it. So now what we do is that like we take the inverse Laplace transform x of t. I'm sure all of us will now know the answer. So it will become x0 times cos of square root of k by m t plus x dot 0 divided by square root of k by m sine of square root of k by m times t. So now we know why omega n is square root of k by m, right? So we can see that the output of the system is going to be an oscillatory signal, and the frequency of oscillation, the angular frequency of oscillation is going to be square root of k by m, right? That's very obvious from this derivation, right? Is it not? Okay, so this implies that omega n is going to be equal to square root of k by m. Okay. So I hope this derivation is clear and the definition of the natural frequency is clear, and how we get the expression for the single degree of freedom mass spring damper system as square root of k. Okay. So now, in fact, I am going to ask you one question, okay, and we will answer this when we come to vertical dynamics, okay, and when we deal with suspension dynamics and analyze ride comfort and pitch and roll and so on, okay. So now you will slowly start seeing the connection between all this mathematics and physics, okay. How do we calculate natural frequencies for higher degree of freedom systems? Natural frequencies for systems whose degree of freedom is greater than or equal to 2. Okay, so we have calculated the natural frequency for a simple system, 1 degree of freedom system, and we have got the expression. Okay, we have applied the definition and we know the formula square root of k by m. Today we just derived it, okay, by applying the definition to the governing. Okay, so I am going to ask you this question as to how we would calculate the natural frequencies of for systems whose degree of freedom is greater than or equal to 2. We will please do find the answer. Okay, if you already know it, you can share it with me. Otherwise, like, please do find the answer. But anyway, we will be looking at this later on, right? So when we are essentially going to deal with suspension. So any thoughts on how we figure out the natural frequency for a higher degree of freedom systems? Let's say we have a 2 degree of freedom system. Right? So how do we find the natural frequency? All right. Okay. So please do find out. As I mentioned, we will learn it. Okay. So as we go on. All right. So now let me pose another question. Okay. Like, this is also like very important from a practical perspective. See, it is important for us to learn all these terms, right? And also like learn what is the physical basis of all these terms, right? So we have looked at natural frequency. We have looked at the definition of natural frequency. Okay. We have also looked at damped natural frequency. See, what was damped natural frequency? As we realized yesterday, damped natural frequency was the frequency at which the output of the underdamped second order system oscillated, right? So that's the damped natural frequency. Okay. Then question becomes, what is resonant frequency? It is so it so turns out that I'm not going to do the derivation. I'm going to leave figuring out the derivation to you as an exercise. If this resonant frequency is meaningful or defined for stable second order underdamped systems whose damping ratio is within a narrow range. Okay, so what is this range? Underdamped systems, okay, whose damping ratio is less than 1 by root 2. Okay, so whose damping ratio is greater than 0, but less than 1 by root 2. Okay, so that is the definition. Sorry, that's when it is meaningful. Okay, so what is the definition of this resonant frequency? Let me write down the definition. It is the frequency of the input, okay, of the input signal of course, it's a sinusoidal input signal at which the magnitude of so-called frequency response of the system. So this brings us to another important class of response, what is called frequency response, which we will discuss shortly. So the frequency response, the magnitude of the frequency response is maximum, okay, for the above class of systems. So what is this above class of systems? The second order underdamped system, stable system, whose damping ratio is between 0 and 1 over 2. Okay, so above class of systems. Okay, so this is extremely important. Okay, so this is the definition. So let me read the definition once again. So the resonant frequency is the frequency at which the magnitude of the frequency response of the above class of systems is maximum, right? So we will see what is this frequency response shortly. But if one were to write down the formula for the resonant frequency indicated by the symbol omega r can be derived as the following. It is omega n times square root of 1 minus 2 zeta square. Of course, once again, it is meaningful only when zeta is between 0 and 1 by root 2. Okay, so that. Okay, so resonance frequency is meaningful only in this range. That is the notion of resonance frequency. Okay. So now this brings us to an important term as to what is called frequency response, right? So yeah, any questions about resonant frequency? No.
So how do we get this value 1 by root 2?
Okay. So essentially, I am not deriving this, but please do watch my notes on videos on control system, right? The NPTEL videos. And there, if you look at the lectures on frequency response, I would have derived that expression. Okay. Yeah. All right. So this is the definition. So what we do is that, like, we will get an expression for the magnitude of the frequency response and we maximize it. Okay. You take the first derivative and equate it to 0, you will. Is that fine? Yes. Hello, am I audible?
Yes, sir.
Okay. So please do refer to that notes and then you will find the reason. Okay, so I didn't want to derive it in this class, but that's the, I wanted to sort of more explain the physics behind. Okay. Yeah.
Okay.
All right. So yeah, any other questions? So in fact, it is, see, people, when we talk about resonant frequency, due to some reason, we sort of get the connotation that, oh, okay, resonance means it's unstable response, like not really. Like say resonant frequency is a parameter that is associated with a stable system. Okay, so you've inputted resonant frequency, output magnitude will be high, but then it will still be bounded. But then it can cause structural damage because if the output magnitude of oscillation is high, it can lead to structural damage. Like so you may see some videos on YouTube also regarding the so-called Tacoma-Narrows bridge collapse, right? Which is a very famous example for resonance, wherein the wind frequency, right, excited the resonant mode and then like the bridge collapsed because the oscillations kept on increasing in magnitude till it reached the maximum value, close to the maximum value, and that causes structural failure. Okay, so it is not desirable. That's a different matter. Okay, but still the oscillations are what to say, high in magnitude but bounded theoretically. Okay? So that's something we need to keep in mind. Okay. So now let's look at this frequency response. So we have looked at step response, impulse response, and so on. What is this frequency response? So if you recall, we considered 4 classes of signals, right? The impulse, the step, the ramp, and the sinusoids, right? So when we talk about frequency response, we are essentially looking at the response of the system to a sinusoidal. Okay, so the system is subjected to a sinusoidal. Okay, so that's when we talk about frequency response. Okay, so it's subjected to a sinusoidal input. So what is this sinusoidal input? Let's say u of t is some u naught sine omega t. Okay, so this is a sinusoidal input whose angular frequency is omega, and u naught is its magnitude. Now there is an important fact. Once again, I am not proving all these things. So once again, if you want to figure out, understand the derivation and the details, please refer to those NPTEL videos on control systems where I've taught all these things in detail. So I'm only going to use these results in this vehicle dynamics course. Okay. So it's a very important point. It can be shown. I'm only using the result once again. It can be shown that when a stable linear time invariant causal dynamic system is subjected to a sinusoidal input it's steady state output. Okay, so we are not talking about the transient output. Once it settles down to a pattern, okay, it's steady state output. Is also a sinusoid. Of the same frequency. But scaled in magnitude. I'll explain what this means, but scaled in magnitude and shifted in phase. All right. So this is an important result. So let me go through it once again very carefully. So it can be shown that when a stable, so once again, point number one, please remember that we are dealing with frequency response where the input provided to the system is a sinusoidal input. In general, let us consider the form of the input to be some u0 sine omega t. That is point number one. Now, I am quoting a result from frequency response, which states that if a stable linear time invariant causal dynamic system, schizo-dynamic system, when it's subjected to a sinusoidal input of the form u0 sine omega t, it's steady state output. So what do we mean by steady state output? You know, like I provide the input, I allow the input transients to settle down, and this output settles down into a steady state pattern. That pattern is also a sinusoid, but more importantly, it's a sinusoid of the same frequency, but it is scaled in magnitude and shifted in phase. This is a property of stable LTI causal systems. And this is an important result because one can use this in experiments. So when we do, in fact, a course on automotive controls, you will do a project where I will give you frequency response data. And using the frequency response data, we will ascertain whether a system can be modeled as a LTI system or not. This is due to this fact. Okay. So what fact? You know, like the fact that, you know, if we have a stable LTI system and a sinusoidal input is provided to it, the steady state output will also be a sinusoid of the same frequency. This is extremely critical. Now, how are we going to use this to our effect? Let's see how we do. So suppose, of course, please pardon my sketching, but then like I just want to explain what is happening. Sorry. So let us say you consider an input sinusoid. Oh, sorry, I think the diagram is not coming out very well. So let's say this is my input sinusoid. Okay, so u of t is in blue color. And let us say y of t. Y of t has some transients, but then after the transients die down, maybe not the, sorry, just give me a second. Let me draw it. So once, let's say the transients die down, but then after the transients die down, the steady state output also is a sinusoid of the same frequency, but it is essentially scaled in magnitude. So you can see the scaling in the magnitude that is happening, and it is shifted in phase. So you can see the phase shift also, which is happening, right? But the frequencies are the same. So that is the consequence of a stable, or that's a unique property of a stable linear time invariant system when it's subjected to a sinusoidal. Okay. So now, in fact, the steady state output, the expression for the steady state output can be written this way. I am writing the final expression based on our discussions. So it is nothing but as time t tends to infinity, what is y of t? That is what we want to find out. And that can be written as u naught. U naught is the magnitude of the input signal, as we already know, times the magnitude of p of j omega. I'll explain what this p of j omega is, multiplied by sine of omega t plus phi. I'll also explain what this one is. Okay, so one can observe that the input magnitude is scaled by p of j omega and shifted in phase by phi, where this phi is phase of p of j. So if you look at this expression, we can observe that the input magnitude u naught is scaled by the magnitude of p of j omega, whereas the sinusoidal pattern still remains, right? So, and the frequency is also omega, as we can see here, but that is shifted in phase by phi. And what is this phi? It is this. So it is this phase of p of j. And what is this p of j omega? P of j omega is obtained when we substitute s equals j omega in the Planck transfer function p of s. Okay, so that's how we get p of j. So let me write down what it is called. This is what is called as a sinusoidal transfer function, p of j. That's the name given. Okay, so I hope this is clear, right? So essentially, let me repeat this important result. So if we have a stable linear time invariant single input, single output system, and we subject it to a sinusoidal input, the steady state output of the system is also a sinusoid of the same frequency, but scaled in magnitude and shifted in phase. So that's what we have done. And in complex variables, so let's say we have a complex variable s, which is written as s plus j omega. How do we get the magnitude? The magnitude is going to be square root of the square sum of the real part square and the imaginary part square, right? The real part is sigma, the imaginary part is omega, right? So this is true for any complex variable. And the phase or the angle is going to be tan inverse of the imaginary component divided by the real component, right? So that's what we are going to get. So this is what we will be getting, right? So as far as the magnitude and phase of any complex variable is concerned. Now the question is, like where would these be useful, right? So before I discuss the answer to that question, let's look at a simple example so that like I convey how do we get these quantities, right? So let us say I consider a very simple example where the Planck transfer function is 1 by s plus 1, right? So I substitute s equals j omega to calculate p of j omega, the sinusoidal transfer function. So this becomes 1 divided by p of j omega plus 1, right? So now, how will I get the magnitude? The magnitude, of course, I have a ratio of two complex variables. It's going to be the magnitude of the numerator divided by the magnitude of the denominator. So the magnitude of the numerator is 1. The magnitude of the denominator is going to be real part square plus imaginary part square, right? So that's going to be 1 divided by square root of 1 plus omega square, right? So that's what I get. Now, if I want to calculate the phase, it is going to be the phase of the numerator minus the phase of the denominator, right? The phase of the numerator is going to be 0 because we have only the real component there, which is it's a positive number plus 1. And the phase of the denominator is tan inverse omega, but then it's in the denominator, right? So we put minus tan inverse omega, right? So I hope it's clear how we got minus tan inverse omega, right? So essentially, this is the magnitude and phase of this particular sinusoidal transfer function. So let me repeat once again. Let's say in this example, if our plant transfer function is 1 by s plus 1, I'm just considering a very simple example, then P of j omega becomes 1 by j omega plus 1, and the magnitude of P of j omega plus 1, or 1 by j omega plus 1 becomes the magnitude of the numerator divided by the magnitude of the denominator, right? The magnitude of the numerator is anyway 1. Magnitude of the denominator is square root of 1. Right? The face of the complex function is going to be the face of the minus the face of the denominator, right? Face of the numerator is anyway 0. Face of the denominator is tan inverse omega, but then I need to subtract because I have the factor in the denominator, right? So 0 minus tan inverse omega, that becomes minus tan inverse omega. Okay, so one can observe something which is very important. So this is the magnitude. Okay, and this is the face. And we have to observe that both the magnitude and phase are functions of the frequency omega, right? So that's something which you and I can immediately realize, right? So both the magnitude and the phase are functions of omega, right? So this is something which we can immediately observe. So, so essentially, how is it practically useful to us, right? So, how is it practically useful? Like what we do is that like if we are given a system, let's say like we are given the steering system, for example, right? And someone asks, hey, look, like I don't have a mathematical model in the form of an ODE, but can you experimentally determine the transfer function? So what I do is that like I will give sinusoidal inputs of varying, measure the output and the input, and then I can get the magnitude and the phase information as a function of omega, but through experiments, and I can experimentally determine the transfer function. Okay, so that's where this concept becomes very useful in practice. And in fact, taking one step, ahead of this, in fact, this exercise, this experiments by giving different frequency, sinusoidal inputs of different frequencies and figuring out whether the steady state output was also of the same frequency will give us confidence whether we can, first of all, approximate a system as an LTA system and then derive the transfer. Okay, so that's where all this theory becomes useful. Okay, so in essence, this concept of frequency response it essentially is very helpful when we want to do what is called as experimental determination of transfer function. Okay, so suppose if we are given a system, we don't know the mathematical model, right? But then like we are asked that, okay, look, like find the transfer function of the system. So then we can use this idea of frequency response to experimentally determine it. Of course, I can always get this transfer function through experiments using an impulse input, right? So if I essentially provide an impulse input and measure the corresponding output, I immediately know the impulse response function, and from there I can get the transfer function. So that's where impulse input becomes very, very important, right? So if I live in a world where I can give a perfect impulse input, I need to do only one experiment, right? So only one input, one experiment, right? To get the impulse response and thereby the transfer function. But then, however, like it's very difficult to generate an ideal impulse input, right? So then what I do is that I can make use of frequency response. So what do I do if I know, if I have a priori, what is the frequency range of interest for the system? First, I give those sinusoidal signals, measure the output, and then I analyze this frequency of the steady state output. If the frequency of the steady state output matches very closely with that of the input, I know that I can I can approximate the system as an LTA system. And once I do that, I also then find out the ratio of the magnitudes of the output and the input, and also the phase difference between the output and this input, the steady state output and the input. Then I can get these magnitude of P of j omega and phase of P of j omega. This is okay. Then from there, I can back calculate what this plant transfer function is. Okay, so that is the idea behind frequency response. But then, like when I want to essentially do frequency response and evaluate the system transfer function, I need to do multiple experiments. Okay, that is the trade-off. Okay, between the impulse response and the frequency response. Okay, so I hope this concept is clear, right? So now, if I were to visualize this two functions, right, the magnitude function and the phase function, this is omega. One of the most common plots is what is called as the Bode plot. Okay, so the Bode plot is a very useful plot to visualize this sinusoidal transfer function P of j. So what is this Bode plot? The Bode plot consists of two subplots. Okay, so the first subplot is what is called as the magnitude plot, wherein, as the name indicates, we are going to plot the magnitude of P of j omega. This is the frequency omega, that is the magnitude plot. The second plot is what is called as the phase plot. Okay, I think I can see a question in the chat box. 1 minute. The phase plot is phase of P of j omega is this one. Okay. So how did we get minus tan inverse of, right? So let me go back to this example. Versus example. Yeah, here it is, right? So now, see what happens is the following, right? So see, when we have this particular factor, right? So the phase of P of j omega, let me write down the intermediate steps. Okay, it is going to be the phase of the numerator minus the phase of the denominator. Okay, the phase of any complex variable is going to be the phase of the imaginary component divided by the real component. Okay, so as far as 1 is concerned, it is going to be 0 by 1, right? The imaginary component is 0. And then the phase of j omega plus 1 is just omega by 1, right? Is it? Okay. The phase, the tan inverse 0 is 0. So then we get minus tan inverse. Is it clear?
Sir, so one more question, sir.
Yes, please.
Sir, in plant function, why we have not used real part? We are always saying plant of j omega only.
Okay. So that is because that's a sinusoidal transfer function. It's a very special transfer function, right? So when we look at sinusoidal inputs, we are only considering the even when you looked at undamped system, right? So and even we take sine omega t cos omega t, we are only going to get factors of the form s squared plus omega squared, right? So we are only looking at the imaginary axis where s is of the form j omega. Okay, that's an intuitive understanding as to why we put s equals j omega and not consider the real part, or consider the real part as 0 when we talk about the sinusoidal transfer function. Okay, so in the transfer function, s is a complex variable. It can have non-zero real parts.
Okay, sir.
So, but when we talk about the sinusoidal transfer function, it's a very special form of s. We only consider s equals j omega. So once again, like if you want to understand the implicit details behind this theory, kindly do watch the videos on control systems. Okay, where would I would have derived. When you go through the derivation, you will understand how this P of j omega came into picture. Okay, so please do watch those videos. Okay, yeah.
Yes, sir.
I have given you a very intuitive understanding. Okay. All right. So now let's come here. So so the Bode plot helps us in visualizing these two subplots. Okay. So in the magnitude plot, what happens is a right. So we essentially plot omega on the x-axis. This is magnitude of P of j omega, but in a unit called decibels. Okay, I will shortly write what this decibel measure is. And in the phase plot, we plot omega on the x-axis. This is the phase of P of j omega in degrees. Okay, so that's what. And what is, of course, in both the plots on the x-axis, we use what is called as a logarithmic scale. So what is a logarithmic scale? If we have a logarithmic scale, if we take any two points that are equidistant from each other, the ratios are the same. Okay. On the other hand, if you use a linear scale, when we use a linear scale, if the two sets of points are equidistant on a linear scale, the differences are equal, right? So that is the bottom line. Okay. So in essence, suppose, let's say, we have a logarithmic scale for a particular variable. Let's say there are three numbers, right? A, B, and C, which are equidistant from each other, right? The distance between A and B is equal to the distance between B and C, right? In a logarithmic scale, B by A is equal to C by B. Okay, so this is the logarithmic scale. Okay, this is the impact. Okay, and if you use a linear scale, suppose in the same plot, we consider a linear scale, B minus A is equal to C minus B, okay, for a linear scale. Okay, so I hope the difference is clear. Now, the question is, why do we use a logarithmic scale for frequency? Due to reasons, okay? So when you use a logarithmic scale, we can cover a larger range of frequencies, okay? That is point number one. And then when we use a logarithmic scale, we can also expand the low frequency regions. Okay, so typically, frequencies in less than 1, right? Let's say in the order of 10 power minus 1, maybe you of interest. Then, if I use a linear scale, imagine plotting 0.1, 0.01 and all, right? It becomes very difficult, right? But then on a logarithmic scale, I can plot from 10 power minus 2, 10 power minus 1, 10 power 0, 10 power 1, 10 power 2, and so on, right? So everything will be equidistant. So I can essentially cover a larger spread of frequencies, right, using a log. And I can also expand into the low frequency. Of course, one limitation is that I can never indicate zero frequency, but that's never needed, right? So what do we mean by a zero frequency sinusoidal signal, right? So consequently, we are not going to be practically interested in omega equals 0 in this discussion, right? So logarithmic scale works out just fine. Now, what is this decibel measure? Just because of the same argument, we use a decibel measure for plotting the magnitude. So what we use in a decibel measure, let me write down what this decibel measure is here. Okay, decibel measure means we take the number and then take the logarithm to the base 10 and then multiply it by 20. Okay, so this is the definition of decibel measure. Okay, so once again, what we can do is that we can cover a larger range of magnitude ratios, magnitudes, and also we can expand into the low value magnitudes, right? When we are analyzing frequency response. So I think that's why we follow this specific unit, okay, of magnitudes. So what we will do, in fact, when you come to a course on automotive controls, I will give you the real data from some automotive applications. You will plot the Bode plot and you will reconstruct the transfer function experimentally. So in this course, we are deriving mathematical equations and deriving the transfer function analytically, right? So, but whatever we learned today is practically very useful. Okay, but to get here, we have to understand the basic concepts, right? That's why we have been spending time on the fundamentals of dynamic systems and transfer functions and so on. We will be doing this exercise as a case study when we come, right? So it's practically very useful. Okay, I can tell that from my own experience and using it for research. Okay, so this is what I wanted to share with you in this class. Are there any questions on the content that we have learned today? All right. Okay. So if there are no questions, let me stop the recording.